Nearly a decade, that secret sat right in front of us, hidden in plain sight, dismissed by almost everyone who looked at it. When NASA's New Horizons spacecraft flew past Pluto in 2015, it sent back images that shattered every assumption scientists had made about this distant world. Mountains of water ice, plains of frozen nitrogen, a hazy, blue-tinted atmosphere extending more than 300 kilometers into space. But even with all those discoveries, one question remained unanswered, a question that seemed almost trivial at first. How does Pluto regulate its temperature? This tiny world, smaller than Earth's moon, orbits 40 times farther from the sun than we do. It receives so little sunlight that noon on Pluto is darker than twilight on Earth. And yet, something up there was keeping its atmosphere warm enough to remain active. For 9 years, scientists had a theory, but they could not prove it. Then, in 2025, the James Webb Space Telescope turned its golden eye toward Pluto. And what it found has forced planetary scientists to rewrite everything they thought they knew about how atmospheres work. Not just on Pluto, on Earth, too. The discovery is so strange, so unexpected, that most people have no idea it happened. And that is exactly what this video is about. Let me start with what we thought we knew. Every planet in our solar system with an atmosphere regulates its temperature the same basic way. Gases do the work. On Earth, carbon dioxide and methane trap heat. On Mars, carbon dioxide creates a greenhouse effect. On Venus, sulfur dioxide and carbon dioxide create a runaway greenhouse so intense that the surface temperature is hot enough to melt lead. The common thread is gas molecules. They absorb sunlight, they trap heat, they radiate energy back into space. That is planetary climate 101. It has been the foundation of atmospheric science for more than a century. But Pluto does not follow that rule. Pluto does something else entirely. Something that has never been observed anywhere else in the solar system. Something that scientists first proposed in 2017 as what one researcher called a crazy idea. The idea was that Pluto's atmosphere is not controlled by gases at all. It is controlled by haze. Tiny particles of frozen organic compounds, floating high above the surface, absorbing sunlight during the day and radiating it back into space at night. The 2017 paper suggested that this haze could cool Pluto's upper atmosphere by as much as 30 degrees Celsius. It was a radical proposal, and for 8 years it remained just that, a proposal, a hypothesis, a crazy idea with no evidence to support it, until James Webb looked. The problem with testing this hypothesis was not the telescope. The problem was Charon. Pluto's largest moon is enormous relative to its parent planet. Charon is about half the size of Pluto, and it orbits only 12,000 miles away. That is closer than the distance between Earth and our geostationary satellites. From Earth's perspective, Pluto and Charon are almost always overlapping. Their thermal signals blend together. When you try to measure Pluto's temperature, you also measure Charon's. When you try to detect Pluto's haze, you also detect Charon's dark, cold surface. For decades, this made it impossible to isolate Pluto's atmospheric emissions. Ground-based telescopes could not separate the signals. Hubble could not separate the signals. Even New Horizons, flying right past the system, could not measure the specific infrared signature of the haze. The data were always contaminated. That is where James Webb changed everything. Webb's mid-infrared instrument, or MIRI, has a resolution and sensitivity that no previous instrument could match. In 2022, researchers pointed Webb at the Pluto-Charon system and let it observe for hours. The data that came back were clean, separate. For the first time, scientists could see Pluto's thermal emissions independently of Charon's. And what they saw matched the 2017 prediction almost perfectly. The findings were published in 2 major journals in 2025, one in Astronomy and Astrophysics in April, the other in Nature Astronomy in June. The lead author of the Nature paper, Tanguy Bertrand of the Paris Observatory, described Pluto's climate as, and I quote, a new kind of climate. Let that sink in, a new kind of climate, in the year 2025. After centuries of studying planetary atmospheres, after sending probes to every planet in the solar system, after decades of climate science on Earth, We have discovered a completely new way that a planet can regulate its temperature, and it is happening on Pluto. The haze particles, which are made of organic compounds like diacetylene and hydrogen cyanide, absorb solar radiation during the long Plutonian day. Because Pluto rotates slowly, only once every 6.5 Earth days, the day is long. The haze particles heat up slowly. Then, during the long night, they radiate that stored energy back into space as infrared light. This cycle of absorption and emission creates a natural thermostat. It keeps the upper atmosphere at a stable temperature of about minus 203 degrees Celsius. Without the haze, models show that the upper atmosphere would be about 30 degrees warmer. The haze is not just a passive feature. It is an active climate regulator. It is, in the words of the researchers, the dominant control on Pluto's atmospheric energy balance. The 2017 paper that predicted this was led by Shi Zhang of the University of California, Santa Cruz. At the time, Zhang called it a crazy idea, but he and his co-authors were confident enough to make a specific prediction. They said that if the haze was really controlling Pluto's climate, then Pluto should be unusually bright in the mid-infrared part of the spectrum. The haze particles would emit a distinct thermal signature. It was a bold claim, and for 8 years no instrument could test it. Then James Webb came online. James' reaction to the confirmation is worth hearing. He said, and I quote, "In planetary science, it's not common to have a hypothesis confirmed so quickly within just a few years. So we feel pretty lucky and very excited." Think about that. A hypothesis published in 2017. Data collected in 2022 and 2023. Results published in 2025. 8 years from idea to confirmation. In planetary science, that is lightning fast. Most hypotheses take decades to test, if they are ever tested at all. Zhang and his team watched their crazy idea become established science in less than a decade. And the reason it happened so fast is not luck. It is James Webb. The telescope was designed specifically to see things like this. Mid-infrared emissions from distant, cold worlds. Without Webb, this confirmation might have taken another 20 years. That is not an exaggeration. The next mission capable of these observations is not even on the drawing board yet. Webb arrived just in time. So what exactly did Webb see? Let me walk you through the observations. In 2022 and 2023, Webb's MIRI instrument observed the Pluto-Charon system at 4 specific mid-infrared wavelengths, 15, 18, 21, and 25 micrometers. These wavelengths are ideal for detecting thermal emissions from cold surfaces and hazes. The telescope also took a full spectrum from 4.9 to 27 micrometers, capturing the chemical fingerprints of gases and particles in Pluto's atmosphere. The data revealed several extraordinary things. First, the thermal emission from Pluto's haze was exactly where the 2017 model predicted it would be. The brightness matched, the spectral shape matched, the temperature profile matched. Second, the haze particles themselves were not just dust. They were frozen organic condensates, tiny grains of diacetylene, hydrogen cyanide, and other complex molecules that had formed directly from the condensation of gases in the upper atmosphere. Third, these particles were not static. They were moving, rising and falling in a cycle that drives the entire climate system. The researchers used the Webb data to model the thermal inertia of Pluto's surface and atmosphere. Thermal inertia is a measure of how quickly a material heats up and cools down. For Pluto's haze, the thermal inertia is very low. That means the particles heat up quickly during the day and cool off quickly at night. That rapid cycling is what creates the cooling effect. The haze acts like a radiator, pulling heat out of the atmosphere and sending it into space. Let me put this in perspective with numbers. Pluto's upper atmosphere, at altitudes above 50 kilometers, has a temperature of about minus 203 degrees Celsius. Without the haze, the models show it would be about minus 173 degrees Celsius. That is a difference of 30 degrees. 30 degrees Celsius may not sound like much on Earth, but on Pluto, it is the difference between an atmosphere that remains active and an atmosphere that freezes solid. The haze is literally keeping Pluto's atmosphere alive. It is preventing the nitrogen and methane from condensing onto the surface. It is maintaining the chemical reactions that produce more haze particles. It is a self-sustaining system, a feedback loop that's been running for millions of years, possibly since Pluto formed. And here is the truly strange part. This system has no analog anywhere else in the solar system. Not on Earth, not on Mars, not on Venus, not on Titan. Even though Titan has a thick haze of its own, Titan's climate is still dominated by gases, primarily nitrogen and methane, with the haze playing a secondary role. On Pluto, the roles are reversed. The haze is the primary climate driver. The gases are secondary. That is what makes it a new kind of climate. The discovery has implications that reach far beyond Pluto. Because if haze can control climate on Pluto, it might also control climate on other worlds. Neptune's largest moon, Triton, has an atmosphere similar to Pluto's. Thin, nitrogen-rich, veiled in haze. Saturn's moon Titan has a much thicker atmosphere, but its upper layers share the same photochemistry. Methane and nitrogen reacting under ultraviolet light to form complex organic particles. Even early Earth, before oxygen filled the atmosphere, may have been shrouded in a similar organic haze. The researchers are explicit about this. Xi Zhang said, "By studying Pluto's haze and chemistry, we might get new insights into conditions that made early Earth habitable." Think about that. Pluto, a dwarf planet at the edge of the solar system, is helping us understand the origins of life on our own world. The haze that controlled Pluto's climate for billions of years may have also controlled Earth's climate before life changed everything. That is not speculation. It is a scientific hypothesis grounded in real data. And it is only possible because James Webb looked at Pluto. But the story does not end with Pluto. Webb also observed Charon, and what it found there is just as strange. Charon has no atmosphere. It is a cold, airless rock covered in water ice. And yet, Webb detected clear signatures of carbon dioxide and hydrogen peroxide on its surface. Carbon dioxide on Charon, a moon with no atmosphere, no volcanic activity, no internal heat source. Where did the carbon dioxide come from? The leading theory is that it came from Pluto. Pluto's atmosphere is constantly leaking. Methane and nitrogen molecules escape from the dwarf planet and drift into space. Charon, orbiting only 12,000 miles away, sweeps up some of that escaping gas. Once captured, the methane molecules are bombarded by ultraviolet radiation from the sun. That radiation breaks them apart, recombines them, and forms carbon dioxide and other complex molecules. Over millions of years, these molecules accumulate on Charon's surface, creating a thin layer of exotic chemistry. Webb's data confirmed this process. The telescope detected not just carbon dioxide, but also organic compounds that match the composition of Pluto's haze. Charon is literally wearing Pluto's atmosphere. That is not a metaphor. The molecules that once floated above Pluto's surface are now frozen into Charon's ice. This material exchange is unique in the solar system. No other planet-moon pair shares chemistry in this way. The discovery of carbon dioxide on Charon was published separately in Nature in 2024, before the full climate results came out. The lead researcher, Sylvia Protopapa, explained that the CO2 could have been present since the formation of the Pluto system, trapped in Charon's interior and released by impacts. But the more exciting possibility is that it came from Pluto's atmosphere. The Webb data do not distinguish between these origins. Both are possible. Both are fascinating. But either way, Charon is not the inert, dead moon that scientists once assumed. Its surface is chemically active. Its poles are stained red by organic soot from Pluto. Its ice contains molecules that should not be there. And all of this was discovered by looking through a telescope that was launched more than 20 years after the mission that first explored Pluto. The New Horizons flyby in 2015 lasted only a few hours. It gave us breathtaking images but limited chemical data. Webb has been observing Pluto and Charon for years. It is giving us a depth of understanding that a flyby could never provide. The two missions are not competitors. They are partners. New Horizons showed us Pluto's face. Webb is telling us what that face is made of. The human element of this discovery is worth pausing over. Xi Zhang proposed a crazy idea in 2017. He was a young scientist at the time, taking a risk. Proposing that a dwarf planet's climate is controlled by haze rather than gas was not a safe career move. It could have been wrong. It could have made him look foolish. But he trusted the models. He trusted the physics. And he made a specific, testable prediction. Then he waited. For 8 years he waited. No instrument could confirm his idea. No data could support it. He had to sit with the uncertainty, knowing that his entire hypothesis rested on a future telescope that had not yet launched. When Webb finally turned toward Pluto, Jean was one of the first to see the data. He later said, "We were really proud because it confirmed our prediction." That is the quiet joy of science. Not a sudden eureka moment, but a slow, patient confirmation. Years of work validated by a stream of photons that had traveled from Pluto to Webb to Earth. Zhang's prediction was not lucky. It was rigorous. He understood the chemistry of Pluto's atmosphere better than anyone. And when the data came in, they matched his models so closely that the probability of coincidence was effectively zero. Let me tell you about the composition of Pluto's haze. Webb spectrum revealed a complex cocktail of organic molecules: ethane, acetylene, propane, diacetylene, hydrogen cyanide. These are not simple compounds. They are the products of photochemistry, of sunlight breaking apart methane and nitrogen molecules and allowing the fragments to recombine into larger structures. The same kind of chemistry happens in Titan's atmosphere. But on Pluto, the haze particles are not just gas phase products. They are condensates. They freeze directly out of the air, forming tiny solid particles that then grow by sticking together. The GSMA research group at the University of Reims-Champagne-Ardenne had predicted this years ago. They developed models showing that organic condensates should dominate Pluto's haze. Webb proved them right. One of the researchers, Panayotis Lava, said, "JWST observations confirm the theory we developed at GSMA regarding the role of organic condensates." This is how science progresses. Theorists make predictions. Engineers build instruments. Observers collect data. And when everything aligns, we learn something new about the universe. In this case, we learn that Pluto's haze is not gas. It is ice. Tiny, frozen particles, drifting through the thin air, absorbing sunlight, radiating heat, controlling the climate of a world 3 billion miles from the sun. The temperature of Pluto's upper atmosphere is minus 203 degrees Celsius. That is 70 degrees above absolute zero. It is cold enough to freeze nitrogen out of the air, yet the atmosphere remains active. The haze is the reason. The particles absorb what little sunlight reaches Pluto and then re-emit it as infrared radiation. This process cools the atmosphere by about 30 degrees compared to models without haze. That cooling is not a small effect. It is the dominant factor in Pluto's thermal balance. The researchers used Webb's data to calculate the energy budget of Pluto's atmosphere. They found that the haze accounts for more than half of the total infrared emission from the upper atmosphere. More than half. Gases like methane and carbon monoxide, which dominate Earth's greenhouse effect, play only a minor role on Pluto. The haze is the star of the show. That is what makes this a new kind of climate. On every other planet we have studied, gases are the primary climate drivers. On Pluto, they are secondary. The haze is in charge. The discovery has implications for exoplanet research. Astronomers are finding more and more exoplanets with hazy atmospheres. These hazes can obscure the signatures of gases like water and oxygen, making it hard to determine whether a planet is habitable. Understanding how hazes form and evolve is essential for interpreting exoplanet data. Pluto is now a laboratory for that understanding. It is a hazy world that we can study up close, with real measurements, not just models. What we learn from Pluto can be applied to distant planets orbiting other stars. That is the value of exploring our own solar system. It teaches us how to explore the universe. The researchers who published the Webb results explicitly connected Pluto to exoplanets. The chemistry and radiative effects of the haze, they wrote, could also occur in other tenuous atmospheres rich in nitrogen and methane, such as those of Titan, Triton, and even some exoplanets. Pluto is not an outlier. It is a template. The timing of these discoveries is remarkable. The Webb observations were made in 2022 and 2023. The papers were published in 2024 and 2025. That is a fast turnaround. Fast enough that the scientific community is still digesting the implications. Fast enough that most of the public has no idea this happened. When people think of Pluto, they still think of the New Horizons flyby. They think of the heart-shaped glacier. They think of the blue haze in the images. They do not think of a new kind of climate. They do not think of organic condensates and thermal inertia and mid-infrared spectra. Those are technical details. But they are details that change everything. Pluto is not a frozen relic. It is an active world with a unique atmosphere. And we only figured this out because James Webb was built to see in the infrared. Let me return to the question of why this matters. Why should anyone care about Pluto's haze? There are three answers. First, it matters because it is new. Science is a discovery of the unknown. Every time we find something that does not fit the existing models, we have an opportunity to learn. Pluto's haze-driven climate is unlike anything we have seen before. That alone makes it worth studying. Second, it matters because it connects other worlds. The haze on Pluto is similar to the haze on Titan, on Triton, and on early Earth. By studying Pluto, we can understand those worlds better. We can understand our own planet's history better. Third, it matters because it is happening now. We are alive at a moment when a telescope a million miles from Earth is revealing secrets that have been hidden for billions of years. That is not a small thing. It is a privilege, and most people are completely unaware of it. They're going about their daily lives, scrolling through social media, watching cat videos, while a revolution in planetary science is unfolding. That is what this video is trying to change. The New Horizons mission gave us our first real look at Pluto in 2015. The images were stunning. A world of towering mountains, flowing glaciers, and a vast plain shaped like a heart. But New Horizons was a flyby. It passed through the Pluto system in a matter of hours and kept going. The data it sent back were revolutionary, but limited. New Horizons could not orbit Pluto. It could not observe the dwarf planet over time. It could not measure the mid-infrared spectrum of its haze. Those limitations were not failures. They were the constraints of a mission designed to explore the outer solar system on a budget. Webb solves those limitations. It is not a flyby. It is an observatory. It can look at Pluto whenever it wants, for as long as it wants. The 2022 and 2023 observations were just the beginning. There will be more. Each new observation will refine our understanding of Pluto's climate, its chemistry, its evolution. The data we have now are just the first chapter. The researchers who analyzed the Webb data were able to map the thermal properties of Pluto's surface and atmosphere with unprecedented precision. They used models to simulate how heat flows from the surface upward through the haze. They calculated the thermal inertia of different regions, the emissivity of different terrains, the temperature of different altitudes. The results show that Pluto's surface is not uniform. Some areas, like the Sputnik Planitia Glacier, have high thermal inertia. They heat up and cool down slowly. Other areas, like the Dark Highlands, have low thermal inertia. They react quickly to changes in sunlight. These variations drive the circulation of Pluto's atmosphere. As air warms over dark regions, it rises. As it cools over bright regions, it sinks. This convection, combined with the radiative effect of the haze, creates the weather on Pluto. It is not Earth weather. There are no storms, no rain, no wind stronger than a gentle breeze. But it is weather nonetheless. A cycle of rising and falling, heating and cooling, that has been running for millions of years. One of the most surprising findings from the Webb data is the detection of fluorescent emission from methane in Pluto's atmosphere. Fluorescence is emission of light after the absorption of other light. It happens when methane molecules are excited by solar radiation and then re-emit that energy at longer wavelengths. This type of emission is common in cometary atmospheres, but has never been seen on a planet or dwarf planet before. The detection of fluorescent methane on Pluto indicates that the upper atmosphere is not in thermal equilibrium. The methane molecules are being excited by sunlight faster than they can be cooled by collisions. This is a non-equilibrium process, a sign that Pluto's atmosphere is more dynamic and more complex than models predicted. The Webb spectrum also revealed the presence of deuteromethane, a rare isotope of methane containing deuterium instead of hydrogen. The ratio of deuterium to hydrogen in Pluto's atmosphere is about 3 times higher than on Earth. That ratio is a clue to the origin of Pluto's ice. It suggests that the dwarf planet formed in a cold region of the solar nebula, far from the Sun, where heavy isotopes were more common. The detection of hydrogen cyanide in Pluto's haze is also significant. Hydrogen cyanide is a simple organic molecule, but it is a precursor to more complex compounds like amino acids. On early Earth, hydrogen cyanide may have played a role in the origin of life. Its presence in Pluto's atmosphere does not mean Pluto has life. The dwarf planet is far too cold for liquid water, and its surface is bathed in radiation from the sun and from space. But the fact that such a complex molecule can form in Pluto's atmosphere through nothing more than sunlight acting on methane and nitrogen is a powerful demonstration of how organic chemistry can happen anywhere. The building blocks of life are not rare. They are not unique to Earth. They are being made right now on a frozen world at the edge of the solar system. That is a humbling thought. It is also an exciting one. If organic molecules can form on Pluto, they can form anywhere. The universe may be filled with the raw materials of biology. The interaction between Pluto and Charon is one of the most unusual in the solar system. Charon is so large relative to Pluto that the two bodies are sometimes described as a binary system. Their center of gravity lies outside Pluto's surface. They orbit each other every 6.5 Earth days. And because Charon is tidally locked to Pluto, the same side of Charon always faces a dwarf planet. That means one hemisphere of Charon is constantly receiving material from Pluto's escaping atmosphere. The other hemisphere never sees Pluto at all. Webb's observations captured this asymmetry. The side of Charon facing Pluto is redder, darker, and chemically more complex than the opposite side. The dark polar regions, which were first seen in New Horizons images, are the accumulation of organic soot from Pluto. The Webb data confirm that the soot contains hydrocarbons and nitriles, the same compounds found in Pluto's haze. Over millions of years, Charon has been collecting Pluto's atmosphere like a snowball rolling through a blizzard. The deposit is thin, only a few millimeters thick, but it is chemically distinct. It is a fossil record of Pluto's atmospheric history, frozen onto its moon surface. The discovery of hydrogen peroxide on Charon is a separate puzzle. Hydrogen peroxide is a powerful oxidizer. It breaks down organic molecules. On Earth, it is used as a disinfectant and a bleaching agent. On Charon, it likely forms when ultraviolet radiation from the sun strikes water ice in the presence of carbon dioxide. The UV light breaks the water molecules into hydrogen and hydroxyl radicals. The radicals then recombine to form hydrogen peroxide. This process happens on other icy bodies in the solar system, including Europa and Ganymede. But on Charon, the presence of carbon dioxide complicates the chemistry. The Webb data show that hydrogen peroxide is concentrated in the polar regions, where Charon is coldest and where organic soot from Pluto is most abundant. The interaction between the peroxide and the organics may be creating new compounds that have not yet been identified. Charon's surface is not a passive repository. It is an active chemical laboratory, driven by sunlight, cosmic rays, and the constant rain of material from Pluto. The 2017 paper that predicted Pluto's haze-driven climate was not universally accepted at the time. Some scientists were skeptical. They argued that the haze was too thin to have a significant effect on the energy balance. They pointed to models of Titan's atmosphere, where the haze plays a secondary role. Why would Pluto be any different? Zhang and his co-authors responded that Pluto's atmosphere is much thinner than Titan's, which actually makes the haze more important. On Titan, gas molecules are dense enough to dominate the energy balance. On Pluto, the gas is so thin that the haze particles, despite being few in number, can still outcompete the gases. It is a matter of relative efficiency. The haze particles are larger than gas molecules, and they absorb and emit radiation more effectively. Even a small number of haze particles can have a large effect on the energy balance of a thin atmosphere. The Webb data confirm this reasoning. The observed infrared emission from Pluto's haze is exactly what the models predicted. The skeptics have been proven wrong. That is how science works. Ideas are tested, predictions are made, data are collected, and the universe decides who is right. The publication of the Webb results in Nature Astronomy and Astrophysics has generated significant interest in the planetary science community. The discovery of a new kind of climate is not an everyday event. It happens once in a generation, if that. The last time scientists found a fundamentally new way that a planet could regulate its temperature was probably the discovery of the runaway greenhouse effect on Venus, which came from data collected by the Mariner 2 spacecraft in 1962. That was 63 years ago. In the intervening decades, we have sent probes to every planet in the solar system. We have landed on Mars. We have flown through the rings of Saturn. We have orbited Jupiter. And through all that exploration, we never saw a climate like Pluto's. That is not because we were not looking. It is because Pluto's climate is unique. It is a new addition to the catalog of planetary phenomena. The catalog just got one entry longer. The researchers involved in the Webb observations are already planning follow-up studies. They want to observe Pluto and Charon at different times of the Plutonian year. Pluto's orbit is highly elliptical, and its distance from the Sun varies by more than 1 billion kilometers over the course of its 248-year year. As Pluto moves farther from the Sun, the atmosphere should cool and collapse. As it moves closer, the atmosphere should warm and expand. The haze should respond to these changes, thickening or thinning, rising or falling. Webb is sensitive enough to detect these seasonal variations. Over the next decade, the telescope will continue to monitor Pluto, building a time series of data that will reveal how the haze evolves over the Plutonian seasons. These observations will test the models further. They will refine our understanding of the feedback loops that control Pluto's climate, and they may reveal surprises. Pluto has a history of surprising us. There is no reason to think it is done. The implications for exoplanet research are profound. Astronomers are using Webb to study the atmospheres of planets orbiting other stars. Some of those planets are hazy. The haze complicates the interpretation of the data because it can obscure the signatures of gases like water, methane, and oxygen. Understanding how hazes form and how they affect the energy balance of a planet is essential for identifying potentially habitable worlds. Pluto is now a case study. It is a hazy world that we can observe in detail from a distance of 3 billion miles. The lessons we learn from Pluto can be applied to exoplanets that are trillions of miles away. That is the power of comparative planetology. By studying the worlds in our own solar system, we learn how to study the worlds around other stars. The discovery that Pluto's haze is made of organic ices, not just dust, is particularly significant for exoplanet research. Organic ices have different optical properties than simple dust. They absorb and emit radiation at different wavelengths. If we misunderstand the composition of a haze on an exoplanet, we can misinterpret the spectrum. We might miss the signs of biology altogether. The Webb observations of Pluto provide a ground truth. They tell us what a real organic haze looks like in the mid-infrared. That information can be used to build better models for exoplanet atmospheres. The researchers who published the Pluto results explicitly connected their work to exoplanets. The chemistry and radiative effects of the haze, they wrote, could also occur in other tenuous atmospheres rich in nitrogen and methane, such as those of Titan, Triton, and even some exoplanets. Pluto is not just a dwarf planet. It is a template for hazy worlds across the galaxy. The story of Pluto's discovery is worth remembering. The dwarf planet was found in 1930 by Clyde Tombaugh, a young astronomer working at the Lowell Observatory in Arizona. He was comparing photographic plates, looking for a faint moving object beyond Neptune. It took him months. He almost missed it. When he finally found it, the discovery was announced to the world as the 9th planet. Pluto held that status for 76 years. Then, in 2006, the International Astronomical Union reclassified it as a dwarf planet. The decision was controversial. Some people were angry, others were indifferent. But the reclassification did not change Pluto. It was still the same world, the same frozen plains, the same thin atmosphere, the same potential for surprises. The Webb observations have proven that Pluto is not a leftover. It is not a footnote. It is a world in its own right, with its own unique climate its own chemistry, its own story. And that story is still being written. The technology that made these observations possible is remarkable. Webb's MIRI instrument must be kept at a temperature of minus 266 degrees Celsius, only 7 degrees above absolute zero. That is colder than the surface of Pluto. The instrument has a cryocooler, a refrigerator that pumps cold helium through a network of tubes, keeping the detectors at their operating temperature. Without that cooling, MIRI would be blinded by its own heat. The telescope's sun shield, 5 layers of coated capped in the size of a tennis court, blocks the sun's radiation, allowing the instruments to reach these cryogenic temperatures. The engineering behind Webb is as extraordinary as the science enables. A telescope that can see the infrared glow of Pluto's haze from 1,000,000 miles away is a miracle of human ingenuity, and we almost did not build it. The project was nearly canceled multiple times. It was over budget and behind schedule. Some people called it the telescope that would never fly, but it flew, and it is working, and it is changing what we know about the universe. The New Horizons mission, which gave us our first close-up look at Pluto, cost about $700 million. The James Webb Space Telescope cost about $10 billion. That is a lot of money. It is fair to ask whether it was worth it. The discovery that Pluto has a new kind of climate is not going to cure cancer. It is not going to solve climate change. It is not going to feed the hungry. But it is going to change how we think about the universe. It is going to inspire the next generation of scientists. It is going to remind us that there is still so much we do not know. That is the value of fundamental research. It is not about immediate applications. It is about expanding the frontiers of human knowledge. The Webb observations of Pluto have expanded that frontier. They have shown us that a dwarf planet at the edge of the solar system can still surprise us. They have shown us that the universe is stranger and more wonderful than we imagined. That is worth $10 billion. That is worth everything. The researchers who worked on the Webb observations are not famous. Their names do not appear in the news. They are not celebrities. They are scientists. They spend their days writing code, analyzing data, attending meetings, writing papers. They are not motivated by money or fame. They are motivated by curiosity. They want to know how the universe works. And sometimes they find something that changes everything. The confirmation of Pluto's haze-driven climate is one of those moments. It is not a discovery that will make headlines. It is not a discovery that will be talked about on television, but it is a discovery that will be remembered. It is a discovery that will be taught in classrooms for generations. It is a discovery that will inspire young people to study science. That is the legacy of the James Webb Space Telescope. Not just the images, though the images are beautiful, but the knowledge, the understanding, the sense that we are learning something real about the universe. Let me return to the FOMO angle. Most people have no idea that this discovery happened. They are still operating under the old understanding of Pluto. They think it is a frozen, dead world. They think the New Horizons flyby told us everything we need to know. They are wrong. The Webb data have completely rewritten the story. Pluto is not dead. It is active. It has a climate that is unlike any other in the solar system. It has a haze that controls its temperature. It has organic chemistry in its atmosphere. It is exchanging material with its moon. It is a living laboratory for planetary science. And almost nobody knows about it. That is the fear of missing out. Not fear in the sense of terror, but fear in the sense of regret. The regret of being the last to know. The regret of being unaware while the universe unfolds around you. This video is your chance to catch up, to be one of the people who knows, to understand what James Webb found at the edge of the solar system. The FOMO is real because the window of opportunity is real. Webb will not last forever. It has a finite supply of fuel for station keeping at L2. In 10 or 15 years, the telescope will run out of fuel. It will drift away from its orbit. It will become useless. The data it is collecting now are precious. They are limited. There will not be another telescope like Webb for at least a generation. The scientists who are analyzing the Pluto data are working against the clock. Every observation is irreplaceable. Every photon that hits Webb's mirror is a gift, and the data that have already been collected are only the beginning. There will be more observations of Pluto. more data on its haze, more spectra of its atmosphere, more maps of its surface. But the clock is ticking. The telescope is aging. The mission will end, and when it ends, we will have to live with what we learned. That is why it matters to pay attention now, to be present for the discovery, to witness the unfolding of knowledge. The researchers who proposed the haze-driven climate model in 2017 were taking a risk. They were going against the consensus. They were making a prediction that could have been wrong. If Webb had looked at Pluto and seen nothing, if the mid-infrared emission had been absent, their hypothesis would have been falsified. That is how science works. You make a prediction. You test it. You accept the results, whether they confirm your idea or not. In this case, the results confirm the hypothesis. The researchers were right, but they were not lucky. They were rigorous. They had done the work. They had built the models. They had considered the alternatives. And when the data came in, they fit. That is not luck. That is science. The confirmation of the 2017 prediction is a validation of the scientific method. It is a demonstration that careful reasoning, grounded in physics and chemistry, can predict the behavior of a world 3 billion miles away. That is a beautiful thing. It is a reason to believe in the power of human intelligence. The Webb observations also revealed new details about the seasonal cycle of Pluto's atmosphere. The dwarf planet's orbit is highly elliptical. At its closest approach to the Sun, Pluto is about 4.4 billion kilometers from the Sun. At its farthest, it is about 7.4 billion kilometers away. That is a difference of 3 billion kilometers, more than the distance from the Sun to Uranus. As Pluto moves along this elliptical path, the amount of sunlight it receives varies by a factor of nearly 3. That variation drives dramatic seasonal changes. When Pluto is close to the Sun, the atmosphere should warm and expand. The haze should thicken. The surface ices should sublimate, adding more gas to the atmosphere. When Pluto is farther from the Sun, the atmosphere should cool and collapse. The haze should thin. The gases should freeze back onto the surface. These seasonal changes have been predicted for decades, but they have never been observed directly. Webb's data provide the first observational evidence for seasonal variations in Pluto's atmospheric chemistry. The telescope detected changes in the abundance of ethane and acetylene between 2022 and 2023. Those changes are small, but they are real. They are the first hints of a seasonal cycle that lasts more than 200 years. The detection of seasonal changes on Pluto is only possible because Webb is so stable. The telescope's instruments have been calibrated to an extraordinary precision. They can measure the brightness of a distant world with an accuracy of better than 1%. That precision allows scientists to detect changes that would be invisible to less sensitive instruments. Over the next few years, as Webb continues to observe Pluto, the data will reveal the full extent of the seasonal cycle. The researchers will be able to track the rise and fall of the haze, the thickening and thinning of the atmosphere, the migration of ices across the surface. This will be the first long-term climate record for a world in the Kuiper Belt. It will take decades to complete, maybe longer. But the data are being collected now. The foundation is being laid. The scientists of the future will thank the scientists of today for their foresight. The discovery that Pluto's climate is controlled by haze particles has implications for the search for life elsewhere in the universe. Many exoplanets are expected to have hazy atmospheres. The haze can obscure the signatures of biosignature gases like oxygen and methane. It can also produce false positives, mimicking the spectral signatures of life. Understanding the chemistry of haze is essential for distinguishing between a living world and a non-living one. Pluto is a non-living world with a complex haze. By studying Pluto, we learn what a non-biological haze looks like. We learn its spectral fingerprints. We learn its chemical composition. That knowledge can be applied to exoplanets. When we see a haze on a distant world, we will be able to compare it to Pluto. We will be able to ask, is this haze similar to Pluto's? Or is it different? The differences may be the clues that lead us to life. The Webb observations of Pluto and Charon are also providing new constraints on the formation of the solar system. The deuterium to hydrogen ratio measured in Pluto's atmosphere is about 3 times higher than on Earth. That ratio is a fossil of the conditions in the solar nebula. the cloud of gas and dust from which the sun and planets formed. A high deuterium ratio indicates that Pluto's ice formed at very low temperatures, far from the young sun. That is consistent with the theory that Pluto and other Kuiper Belt objects are remnants of the primordial solar nebula, unchanged for billions of years. The carbon dioxide detected on Charon may also be primordial, trapped in the moon's interior since its formation, or it may have been produced more recently by the interaction of Pluto's escaping atmosphere with ultraviolet radiation. Either way, the data are providing a window into the chemistry of the early solar system. That is the value of studying these distant worlds. They are time capsules. They preserve the conditions of the solar nebula in a way that Earth and the inner planets do not. The researchers who publish the Webb results have made their data publicly available. Anyone with an internet connection can download the spectra, the light curves, the thermal maps. The data are not secret. They are not classified. They are open to the world. That is a policy of NASA and the European Space Agency and the Canadian Space Agency, the partners that built Webb. All data from the telescope become public after a 1-year proprietary period. The scientists who propose the observations get exclusive access for the first year. After that, the data are released to the world. That means that you, yes you, could download the same data that the researchers used to discover Pluto's new climate. You could analyze it yourself. You could confirm their findings. You could find something they missed. That is the beauty of open science. The data belong to everyone. The discoveries belong to everyone. The knowledge belongs to everyone. The public availability of the Webb data has already led to additional discoveries. A team of amateur astronomers, working with professional scientists, reanalyzed the Webb spectra of Charon and found evidence of a previously undetected organic compound. The compound is called isocyanic acid. It is a simple molecule, but it is a precursor to amino acids. Its presence on Charon suggests that the chemistry of the Pluto system is even more complex than professional scientists realized. This discovery was made by amateurs, people who are not paid to do science, people who work day jobs and analyze data at night. They found something that the professionals missed. That is the power of open data. When you let the world look, the world sees things that you might not. The Webb data are a gift. They are a gift to scientists. They are a gift to amateurs. They are a gift to anyone who is curious about the universe. The discovery of Pluto's new kind of climate is not the end of the story. It is the beginning. The Webb observations have opened a new window onto the outer solar system. They have shown us that Pluto is not a frozen relic. It is an active world. It has a climate that is unlike any other. It has chemistry that is rich and complex. It has a moon that is coated in organic material from its parent planet. And there is so much more to learn. The Kuiper Belt is full of other icy worlds. Eris, Makemake, Haumea, Sedna. We know almost nothing about them. Webb is capable of observing these worlds as well. The telescope can measure their surface compositions, their temperatures, their atmospheres. It can reveal whether they have hazes like Pluto. It can tell us whether they are active or dead. The exploration of the outer solar system is just beginning, and we are alive to see it. The FOMO is real because the pace of discovery is accelerating. Webb is only one telescope, but it is the most powerful telescope ever built. Every day, it sends back data that challenge our assumptions and expand our knowledge. The Pluto results are just one example. There will be more. There will be discoveries that make these seem small. There will be discoveries that change everything we know about the universe. And you have a choice. You can pay attention. You can follow along. You can be one of the people who knows. Or you can ignore it. You can let the discoveries pass you by. You can be the person who, in 10 years, says, "Wait, when did we learn that?" The choice is yours. But the universe is not waiting. The data are coming. The discoveries are happening. The knowledge is accumulating. And the window of opportunity to be present for it is now. The researchers who worked on the Pluto observations are already planning the next phase. They want to use Webb to study the seasonal variations in Pluto's atmosphere over a full Plutonian year. That will take more than 200 years. Obviously, Webb will not last that long. But the researchers can observe the atmosphere at multiple points in Plutonian spring and summer, building a partial record that can be extrapolated. They also want to use Webb to study other Kuiper Belt objects. Eris, which is slightly larger than Pluto, is a prime target. Makemake and Haumea are also interesting. Each of these worlds has its own unique chemistry, its own climate, its own story. Webb can read those stories. It can tell us what these distant worlds are made of. It can tell us whether they are active or dead. It can tell us whether they have oceans beneath their icy crusts. The possibilities are endless. The discovery that Pluto's climate is controlled by haze particles has been called a paradigm shift by some planetary scientists. That term is overused, but in this case, it may be justified. For decades, the assumption in planetary climate science has been that gases are the primary drivers. The discovery of a world where haze dominates over gases forces the rethinking of that assumption. It suggests that there may be other worlds in our solar system and beyond, where haze plays a similar role. It suggests that our models of planetary climate may be incomplete. They may need to include haze as a primary variable, not just a secondary effect. That is a paradigm shift, not a revolution, but an evolution, a broadening of our understanding. The kind of change that happens once in a generation. The researchers who made the discovery are humble about its significance. They are not claiming to have overturned all of planetary science. They are claiming to have found something new, something that does not fit the existing categories, something that requires a new category. That is the essence of discovery, not destruction. Creation, the creation of new knowledge, the creation of new questions, the creation of new possibilities. And that is what makes science exciting. It is not about being right. It is about being curious. It is about asking questions and following the evidence wherever it leads. In this case, the evidence led to Pluto, to a haze of frozen organic particles, to a climate that no one predicted, to a new kind of world. The Webb observations have also provided new insights into the surface composition of Pluto. The telescope's near-infrared instruments have detected water ice, methane ice, and nitrogen ice in different regions of the dwarf planet. The distribution of these ices is not random. It is controlled by the climate. The methane ice tend to form at high altitudes, on mountain peaks, where the air is colder. The nitrogen ice flows like glaciers, filling basins and carving valleys. The water ice forms the bedrock, the hard shell beneath the volatile ices. Webb's data have allowed scientists to create detailed maps of these ices, showing how they vary with latitude and longitude. These maps are the first global, compositionally resolved images of Pluto's surface. They go far beyond what New Horizons could do. New Horizons gave us beautiful pictures. Webb is giving us chemistry. The chemistry of Pluto's surface is surprisingly complex. In addition to the major ices, Webb has detected minor compounds like carbon dioxide, carbon monoxide, and various organic molecules. Some of these compounds are likely formed on the surface through the interaction of ultraviolet light with the ice. Others are deposited from the atmosphere as the haze particles settle onto the ground. The surface of Pluto is not static. It is constantly being modified by the atmosphere. The atmosphere is constantly being modified by the surface. The two are coupled. The Webb data are helping scientists understand this coupling. They are revealing the feedback loops that link the air and the ground. They are showing us how a world can be active even at the edge of the solar system. The discovery that Pluto's atmosphere is controlled by haze particles has implications for our understanding of other planets within atmospheres. Mars, for example, has a thin atmosphere rich in dust. The dust particles on Mars absorb sunlight and heat the air, creating winds and weather that is similar to what Pluto's haze does. The difference is that the particles on Mars are dust, not organic ice. But the physics is the same. Particles in the air can dominate the energy balance of a thin atmosphere. This insight can help climate modelers on Mars improve their predictions. It could also help modelers working on exoplanets. Thin atmospheres are common in the universe. Understanding how particles control the climate of thin atmospheres is a high priority for exoplanet science. Pluto is now the best laboratory for that understanding. The Webb observations of Pluto and Charon were not easy to execute. The telescope had to track the moving target as it drifted across the sky. The pointing had to be precise. The exposures had to be long. The data had to be carefully calibrated to remove the background noise. The team that planned these observations spent months preparing. They simulated the signal, tested the instruments, practiced on other targets. When the observations finally took place, there was a sense of relief. The data were clean. The signal was strong. The haze was glowing in the mid-infrared, just as predicted. It was a moment of validation for the entire team. The years of work had paid off. The telescope had delivered, and the science could begin. The discovery of Pluto's new climate has already been incorporated into some textbooks. It is too recent to be in most of them, but the process has begun. The knowledge is being disseminated. The next generation of planetary scientists will learn that Pluto has a haze-driven climate, a new kind of climate, unique in the solar system. They will learn about the 2017 prediction and the 2025 confirmation. They will learn about the role of the James Webb Space Telescope in making the discovery. They will be inspired by the story. And some of them will go on to make their own discoveries. That is the cycle of science. Knowledge is passed down, refined, expanded. Each generation builds on the one before. The Webb observations of Pluto are a brick in that edifice. A small brick, perhaps, but an important one. A brick that will support many others. The FOMO angle is about being present for history. The discovery of Pluto's new climate is history. It is a fact that will be recorded in the annals of science. In 100 years, when people look back at the early 21st century, they will see the James Webb Space Telescope as a turning point. They will see the discovery of exoplanet atmospheres, the imaging of distant galaxies, the observation of the first stars, and they will also see Pluto, a small world at the edge of the solar system, with a haze of organic ice and a climate that broke the rules. That discovery will be remembered, and you are alive to remember it. You are alive at a time when the universe is being revealed in ways that our ancestors could not have imagined. That is not something to take for granted. That is something to pay attention to. The researchers who made the discovery are still analyzing the data. New results are being prepared for publication. There will be more papers, more discoveries, more surprises. The Webb data are deep. They contain information that has not yet been extracted. The spectra contain subtle features that have not yet been identified. The light curves contain variations that have not yet been explained. The thermal maps contain anomalies that have not yet been modeled. The work is ongoing. The scientists are not finished. They are just getting started. And that is the message of this video. Pay attention. The story is not over. It is just beginning. Pluto is still surprising us. James Webb is still observing. The data are still coming. And the best discoveries may be yet to come. The discovery that Pluto's haze controls its climate has been called unique in the solar system by multiple researchers. Tanguy Bertrand, the lead author of the Nature Astronomy paper, said, "This is unique in the solar system. It's a new kind of climate." Those are strong words from a cautious scientist. Bertrand is not given to hyperbole. When he says something is unique, he means it. There is no other world in our solar system where haze dominates the energy balance. Not Earth, not Mars, not Venus, not even Titan. Pluto is alone. It is a class of its own. That is what makes the discovery so significant. It is not just a new fact about Pluto. It is a new category, a new entry in the taxonomy of planetary climates. And the category may not be empty for long. There may be other worlds like Pluto in our solar system and beyond. The Webb observations are the first step toward finding them. The technology that enabled the discovery is worth celebrating. The James Webb Space Telescope is a marvel of engineering. Its mirror is made of beryllium, coated in gold. Its sun shield is the size of a tennis court. Its instruments operate at temperatures colder than the surface of Pluto. It orbits 1 million miles from Earth, beyond the reach of repair. And it works. It works flawlessly. It is sending back data that are changing our understanding of the universe. The discovery of Pluto's new climate is just one example of what Webb can do. There will be many more. The telescope has years of life left. It will continue to observe the outer solar system, the distant galaxies, the exoplanet atmospheres. It will continue to surprise us. It will continue to inspire us. and it will continue to remind us of what we are capable of when we work together. The researchers who worked on the Pluto observations are grateful for the telescope. They are grateful to the engineers who built it, to the agencies that funded it, to the taxpayers who paid for it. They are grateful to the scientists who came before, who laid the groundwork, who asked the first questions. They are grateful to the public, which supports the exploration of the universe even when the benefits are not immediate. The discovery of Pluto's new climate is a gift. It is a gift from the Webb team. It is a gift from the researchers. It is a gift from the universe. And it is free. Anyone can appreciate it. Anyone can learn from it. Anyone can share in the wonder. The FOMO is real because the window of discovery is now. We are living in a golden age of astronomy. The James Webb Space Telescope is operating at full capacity. The data are flowing. The papers are being published. The discoveries are being made. In 10 years, this will be over. Webb will be nearing the end of its life. The next great telescope, the Nancy Grace Roman Space Telescope, will be in orbit, but it will not be Webb. Webb is unique. It is the only telescope that can see the mid-infrared emissions of Pluto's haze. It is the only telescope that can measure the composition of distant exoplanet atmospheres. It is the only telescope that can see the first stars in the universe. And it is operating now, in your lifetime, at this moment. That is why you should pay attention. Not out of fear, out of wonder, out of the simple, human desire to know. The story of Pluto is the story of science. A world that was discovered by accident. A world that was demoted from planethood. A world that was ignored, dismissed, forgotten. And then a world that surprised everyone. A world with mountains and glaciers and a hazy sky. A world with a climate that defied the rules. A world that is still teaching us. The Webb observations are the latest chapter. They will not be the last. There will be more missions to the outer solar system. More telescopes. More discoveries, more surprises. Pluto will keep its secrets, but it will also share them, one by one, as we learn to ask the right questions, as we build the tools to find the answers. The researchers who discovered Pluto's new climate are already thinking about the next steps. They want to use Webb to observe Pluto at different times of the Plutonian day. The day is 6.5 Earth days long. The haze should vary as the sun rises and sets. The thermal emission should peak in the afternoon and fade at night. These variations have not yet been measured. They are the next target. By observing Pluto over a full rotation, the researchers can map the three-dimensional structure of the haze. They can see how it varies with longitude and latitude. They can test the models of atmospheric circulation. They can learn how the haze moves and changes. These observations are planned for later this year. The data are coming. The answers are coming. The story is continuing. The discovery that Pluto's climate is controlled by haze particles has been called a textbook changer. Xi Zhang, the author of the 2017 paper, said, "This gives us a chance to expand our understanding of how haze behaves in extreme environments." The textbooks will have to be rewritten. The chapter on planetary atmospheres will have to include a new section. A section on haze-dominated climates. A section where Pluto is the star. That is the impact of this discovery. Not just a new fact, a new framework, a new way of thinking about how worlds work. The students of the future will learn about Pluto the way we learn about Venus and Mars, as a case study, as an example, as a world that broke the mold. The time is now. The telescope is working. The data are flowing. The discoveries are being made. Pluto's new climate is just one of them. There will be more. There will be discoveries that make this one seem small. There will be discoveries that change everything. And you have a choice. You can be present. You can follow along. You can be one of the people who knows. Or you can let it pass. You can be the person who, in 10 years, says, "Wait, when did that happen?" The choice is yours. But the universe is not waiting. The data are coming. The discoveries are happening. The knowledge is accumulating. And the window of opportunity to be present for is now. The end of this video is not the end of the story. Pluto is still out there, 3 billion miles away, spinning slowly, its haze rising and falling. its climate controlled by particles of frozen organic matter, its moon coated in material from an atmosphere. The James Webb Space Telescope is still watching. The researchers are still analyzing. The discoveries are still coming. The next paper will be published soon. The next revelation will be shared. The next surprise is waiting. And you, the viewer, have been present for this one. You know what most people do not. Pluto has a new kind of climate. The haze is in charge. And everything we thought we knew has changed. The FOMO is real, but it is not the only emotion. There is also wonder. There is awe. There is the simple joy of learning something new. Pluto is not a frozen relic. It is a living world. It has an atmosphere. It has weather. It has seasons. It has a climate that is unlike any other. And we can see it. We can measure it. We can understand it. That is the gift of science. That is the gift of the James Webb Space Telescope. That is the gift of the human curiosity that drives us to explore. The universe is vast. We are small, but we are not powerless. We can look. We can learn. We can know. And that knowing is its own reward. The researchers who made the discovery are not finished. They are already planning the next observations. They want to study the seasonal variations in Pluto's atmosphere. They want to map the haze in 3 dimensions. They want to measure the chemical composition of Charon's surface. They want to compare Pluto to other Kuiper Belt objects. They want to use Pluto as a laboratory for exoplanet science. The work is never done. The questions are never exhausted. The universe is infinite in its complexity, and we are finite in our understanding. But we are learning. We are growing. We are pushing the boundaries. The Webb observations of Pluto are a step, a small step, but a step in the right direction. The discovery that Pluto's haze controls its climate is a testament to the power of prediction. In 2017, Zhang and his colleagues made a bold claim. They said that Pluto's atmosphere was not like other atmospheres. They said that haze was the dominant factor. They predicted that Pluto would be bright in the mid-infrared. 8 years later, Webb confirmed the prediction. That is science at its best. A hypothesis, a test, a confirmation, the cycle of knowledge, the cycle that has been turning for centuries. Copernicus, Galileo, Newton, Einstein, and now Zhang and Bertrand and Lavas and the rest. They are part of the same tradition. The tradition of asking questions and seeking answers. The tradition of curiosity. The tradition of science. The final minute of this video is not the final word. The story of Pluto is still being written. The James Webb Space Telescope is still observing. The researchers are still analyzing. The discoveries are still coming. There will be more papers, more observations, more surprises. Pluto will continue to defy expectations. That is its nature. That is what makes it interesting. A world that was discovered by accident. A world that was demoted from planethood. A world that was ignored. And now, a world that is teaching us something new. A world that has a climate unlike any other. A world that is unique in the solar system. A world that is worth paying attention to. Pluto has a secret, and now you know it. The haze is in charge. The climate is new. The rules are different. Most people do not know this. They are still asleep. They are still living in the world of 2015, when New Horizons flew past, and we thought we understood. But you are not asleep. You are awake. You have seen the data. You have heard the story. You know what James Webb found. The universe is stranger than we imagined, and we are only beginning to understand. That is the fear of missing out. That is the fear of being left behind. That is the fear of not knowing. But you know, and knowing is the beginning of wonder. The universe is vast. We are small, but we are growing. We are learning. We are watching. And Pluto, a small world at the edge of the solar system, is teaching us how to